Okay. Okay, today we are going to give an overview of Fourier series analysis, of how was the uses of Fourier analysis, and what we are going to observe, or what we are going to see, is that any function, it can be an odd function or an even function, and these, we can express these as decompositions in sines and cosines. So we're going to discuss about this topic, and the general idea is to describe any function f of x as a constant value a half of a0 plus a summation of terms from 1 to infinity of an cosine nx plus the summation of some terms bn times sine nx, okay? And n, it goes from 1 to infinity. So now this n, so this n would start from 0, but the 0th term, it will appear actually as a constant term, which is right here. And now, so this is how we define the initial problem. If this is the definition of the initial problem, this is an equation. And what we need to determine is we need to determine these coefficients here, a0, an, and bn. Because sine and cosine, they are well-defined functions, so our initial effort is this one. And we can say that these values, a0, an, bn, they are functions of f of x. They depend on f of x. So they're defined in terms of f of x. So, and then we have a couple of conditions, a few conditions on f of x. First of all, f of x, it can allow only a finite number of discontinuities. So you cannot have infinite number of discontinuities, but a countable amount of discontinuities, it's fine, we can deal with it. So you can assume that we have a function which is undefined, let's say x is equal to 2, fine, we can calculate the Fourier series for it. And then, other than this, we can say that, I think this would be most of it. But this can also mean that the function f of x can have a finite number of maxima and minima in a certain range. Because any function can have an infinite number of maxima and minima. Now, when we see this expansion, what we can do is that we can remind ourselves that similarly, this since sine of x and cosine of x, since they can be expressed, they are oscillatory function or time harmonic function, or it doesn't have to be only time, we can also call them space harmonic functions. We know that these can be written, so based on this important quantity, e to the power I phi theta, this is equal to cosine theta plus I times sine theta. So knowing this, we can state that any function can be described, and we're going to say also as exponential functions. That's one way to put it. And in order, when we do this Fourier series analysis, we have some properties, and these properties, they depend only on the integrability, or the way that how the integrals of sine and cosine behave. So we can say that over a specific period, from minus pi to plus pi, the sine mx, sine nx, dx, this is equal to pi times the Kronecker delta mn, okay? So this is the integral of sine with a specific frequency times another sine with a different frequency. If we integrate them together, we get pi times delta mn, and delta mn, it is a function which is equal to 0 if m is different from n, and it is equal to 1 when m is equal to n. Okay, so this is the Kronecker delta function. This is the specific function. Then similarly, we can also write the same thing for cosine mx sine nx dx, this is also equal to pi delta mn. Okay, so the same pattern appears. And at this moment, we can say that, for example, if we have here cosine 2x, sorry, I have a mistake here, this should be cosine, sorry, this is cosine. So here we can say that sine mx and sine 2x times sine 2x dx, this means that it's going to be equal to pi, okay? I have a couple of comments here in the class. Evando, cila pjesë e tabelës nuk duket?
Se kalove, nga ana e majt, do më thonë nga fillimi, nuk duket mirë. Pjesa kur
Okay, we have a comment here from regarding the quality of the board.
Do më thonë qoftë është e mundur ta spostosh ose ta
So we can leave these comments for your comments that are online. So let's continue here, and I hope the registration will be fine. So I'm just asking from okay, I think we can continue. Okay, so this is what we can say, and similarly we can add that the integral of sine mx cosine nx, this is always going to be 0 independently of the values of m and n. Now, this is one way to put it, but actually imagine for a moment if n is equal to 0, where this integral is always over a full period, from minus pi to pi. So imagine for a moment if cosine is equal to 0, you get cosine 0 is 1, and we may wonder what is the integral of sine mx, and in fact we know that here, based as a from here we can also state the following, that the integral of any function between a full domain, a full 2 pi range, this can be of sine mx dx, this can be equal to, this is going to be equal to 0, and similarly also cosine mx dx, this is again equal to 0. So these two new functions that we wrote here, you can also read it from this aspect. So just assuming in this expression, set n is equal to 0, you get 1. Here, you set n, what can you set n? M. So let's say when m, when is this equal to 1? Sorry, I've forgotten dx here. This is equal to 0. And probably this is also clear because we know how a function looks like. So I have to pick this up. Hello. Hello. Okay. We have a student just asking for the information of the class, so we can continue here. So from here, you know that we know how sines look like. So sine over a full period is going to look like this, and we know that integral over a complete period is going to be equal to 0, because here we have a positive value, here we have a negative value, and finally this is what we obtain. Now, but we observe here that we have a certain orthogonality relationship here. Okay, so we can use these orthogonal expressions to find what is an and bn. Okay, so we should make use of these, and that's exactly what we are going to do. And for this, probably we can use this part of the board. I think we don't have much. So, in order So here we can define, or we can see that if you want to determine, let's say, A1, if you want to say that if A1 is equal to find what this is, we notice that this A1, this corresponds that when n is equal to 1. And this means that what we can do is that we can multiply with sine x, because when n is equal to 1, we obtain a term. So here we have cosine x, okay, in this expression. Then we can multiply everywhere with another function, which is, here we have cosine x. We can multiply here also with cosine x, and here with cosine x, cosine x, cosine x, and this way we can integrate all of these expressions. Okay, once we integrate all of these expressions, we know that from this summation we are going to have terms that look like the following. Let's have a look here on the board. So here we're going to have, let's observe just this term here. From the expansion, we get A1 times cosine x times cosine x plus A2 cosine 2x times cosine x plus A3 cosine 3x times cosine x. So this complete expansion of the series, we are multiplying with this new factor. Okay? But once we multiply with this factor, and then we integrate all of these, and we should not forget that the integral is from minus pi to pi. And in fact, this integral from minus pi to pi, the important thing is the complete range. You might see this one also like this, from 0 to 2 pi. It's not that we're going to integrate in the same expression from both domains, but it could either be from minus pi to pi or from 0 to 2 pi. For the moment, let's keep this one as the domain. And then, based on the orthogonality relationships that we got here, it looks like this expression, we can get the A1, we can get this out, but this is going to be A1 times pi, okay, from this integral. From this integral, since two cosines with different frequencies, their integral is going to be equal to 0, so this term will be gone. Okay, so these are gone. So it looks like from this expression, we find A0 cosine x, we multiply this one over the complete domain. So this is a constant. We have here A0 divided by 2 times cosine x dx from minus pi to pi. This is 0. I think we wrote this one before a while. Plus, we have this whole series, but all the terms except the very first one are 0. So it looks like we are kind of simplifying this expression. And then we have here plus b1 sine x cosine x plus b2 sine 2x cosine x. And all of these terms, we keep integrating again. And we just saw that sines and cosines, they are always orthogonal with respect to each other. So their integral is going to be equal to 0. So all of these terms, they will vanish. So this expression, this will be gone. So we won't have this one after we multiply with cosine x and we integrate over these. So actually, let me have it like this, right? Here, here, and here. So finally, it looks like we have the following. The integral of the function f of x times cosine x dx, the integral from minus pi to pi, this is going to be equal to, so we got this one, we're integrating this expression, a0 divided by 2 times cosine x, and integrating it, we get 0, so this term will be gone, plus this whole series expansion from 0 to infinity. If we multiply them like this, we are left only with this term, so we get here, this is equal to a1 times pi. I think this is all. okay? And all the rest are 0, including these. So it looks like finally that's all we get. Okay? So we observe that as a result here we have that A1, this is equal to 1 over pi times the integral from minus pi to pi of f of x cosine x dx. Okay, so this is only for A1. Similarly, we can write that for any A, so we can generalize this expression or this expression here. We can find that AN is equal to 1 over pi times f of t, or we can call this one f of x cosine nx dx. So this is what we can get from AN, and as we can see, it's simply the generalization of this one, because if the frequency in the cosine was slightly different, when we say slightly different, this would have been cosine 3x, then this term would cancel out. But we have to notice that if we want to find the A3, we have to multiply, if we need to find the A3, we have to multiply all these terms in this expression with cosine 3x, and then we integrate, okay? So, so we found what is AN, and then similarly, I think we can argue that also Bm, or Bn, this can be number n, this is also equal to 1 over pi, the integral from minus pi to pi, f of x sine nx dx. Okay? So this is how we can find all these constants, and apparently this is how we find them. Now, inserting these two expressions into here, it is the complete Fourier series expansion of this specific function. Now, it looks like to get the Fourier series expansion, we need an infinite number of terms, okay? And this is a major question. The first moment that we are posed with such an issue, it looks like we need an infinite number of terms, and this is not very feasible because we don't have an infinite amount of paper to write on it, and at the same time, we don't have a computer that can store infinite number of terms similarly, right? So this is an initial worry that we have to consider, and if we look at an example, we can figure out, it's good to go over one example and see what we get. Ledio, how is the board? Can you comment on the board? On the registration, do you see the board nice?
Jo, besoj nuk e shikojmë të plot.
Ledio, can you hear my voice? But can you hear me? Okay, is the sound good? Okay, good. We have to do this technical testing. But which part of the board do you see? Do you see? Okay, ladies or Evaldo, can you help me here? Do you see this part? I know, Ledio. Okay, but the board, can you comment on the board? So I guess you see up to here, right? That's where I see this board. Do you see this part, which I'm drawing a line here? Ledio, I'm waiting for your comments. It should be okay. You should see the board, right? Okay, so you see this line. You see my hand, right? But do you see what I'm drawing here, right? Do you see here? Okay, so yeah, I probably don't see the whole board, but we'll try to use a specific area of the board. Yes, I'm sure that it's a little limited. Okay, so then we can continue then. So we started a discussion of how we can express or how we can decompose a function as in terms of sines and cosines. Now, this initial expression that we wrote here, it is modified a little because we're modified with cosine and sine terms. But now, let's try to identify how to write the expansion of a function. Probably we can erase this one. We need this space. So we need to find, so the question is the following. Let's assume that we have a function f of x, which is equal to x, and x is from 0 to pi, and this is x minus 2 pi, from pi to 2 pi. Now, it's always best if we have some equal sign to understand actually what we really have. And when we look at this function initially, this means that we have, this is equal to x, this is pi, and this is 2 pi, and this function of x, it goes like this, so it's a linear function. It's a linear function. The other side, this is equal to, when x is equal to pi, x minus 2 pi, we get here a value of minus pi. So this is pi, this is minus pi, so we get a point down here. And it goes also with the same slope, okay? Because this is x minus 2 pi, is the same function, this would continue initially like this, right? If we had this f of x is equal to x, but the moment that we subtract 2 pi, imagine you are just finding this line immediately down here. So this is our function, okay? This is the function, and let's notice that this is not continuous. Now, this function, we want to express this as we want to find the Fourier series expansion. In order to do this, it is always, often, it is better if we define the range, not from, maybe I can write it like this. Instead of having to integrate from 0 to 2 pi, often it is easier to integrate from minus pi to pi. We are using this terminology, the need to integrate, when we're doing Fourier analysis, because we have to integrate in this domain. Okay, so instead of having this reference, we can skip to here. So we can shift these values of the function, and we can have this new domain, and then our new function is going to look like this. Okay, this is it. In black, it was as it was defined here. Now here we can redefine as a function of x, and now this is going from minus pi to pi. Now, once we have this, we need to identify, or we see that this series expansion, we can, wait a second, I just need to, okay. So we need to find, as we said, the AN and BNs. And the AN, we just erased it before a while. AN, it was equal to 1 over pi times the f of x cosine nx dx. Okay, this was this function. The AN, and for A1, this would be 1 over pi times x cosine x dx. Okay, and the integral is from minus pi to pi. So we notice that this function, x cosine dx, this is an odd function. Okay, so if we look at this function here, this is odd. It is not an even function. And odd because we have that if this is the the coordinate system, we are integrating from this point to this point, from minus pi to pi. We have the cosine, it's going to look something like this. I guess I'm right, okay, because cosine of 0 is equal to 1, cosine of pi is equal to, this is minus 1, and cosine of minus pi, what is this function actually? Cosine x, cosine of 0 is 1, at pi, cosine pi over 2 is 0, so we're going to get something like this. I did a mistake. It's going to be like this and like this. Okay. So, yeah, this is the correct. This is cosine x, and this is an even function. Now, x, that we multiply this cosine x, it is an odd function. And it's something like this. And we know that the product of an odd function times an even function, so this is odd, the product of odd function and even function, this is going to be another odd function. The odd function is equivalent, like integrating this function from this range to this range, and it's pretty obvious that here we get a negative contribution, here we get a positive contribution, and overall, this A1, this is simply going to be equal to 0. Okay? So this is the A1, and the B1 is going to be equal to 1 over pi times x sine x dx. When we look at this function, x, this is odd, so an odd function times an odd function, we get an even function. So from the integral, we expect to get some values which are different from, let's say, they are different from 0. So at this point, we can simply say that you can use this integral, if we want to integrate here, x sine x dx, x sine x dx, we can use this u dv is equal to uv minus v du. So we can use the rule of substitution. So if we follow a couple of steps, we can simply move forward. We can say that u is equal to x dv would be sine x dx, and here we can determine also what is du. Du will be equal to dx, and v would be equal to cosine x. So finally, what is the integral of sine x? Integral of sine x is minus cosine x. So here we have u times v, and u times v is a product of these numbers. So it's minus x cosine x, or minus pi to pi, minus the integral of v du. V is minus cosine du, it's dx. Okay. So it looks like now the cosine of the integral of cosine x dx, this is equal to sine x. So overall, all this integral, this is something like 1 over pi. Okay, we're just trying to determine the p1. This 1 over pi is going to be equal to x cosine x minus x cosine x plus sine x, and the limits of integration, they are from minus pi to pi. You can correct me if I do any mistake, but it looks like this 1 over pi, this is going to be equal to, so if you substitute the values, this is minus pi, cosine pi. What is the cosine of pi? It's minus 1. So we get here minus 1. So this is going to be pi plus sine pi is equal to 0, so this is all, And from here, we have to subtract the value of this function at x equal to minus pi. So sine of minus pi is minus 1. Minus 1 times minus 1, it's 1. 1 times minus pi, it's minus pi. Then we have here plus sine of minus pi. Sine of minus pi, we know that pi is here. Sine at this point is equal to 0. So finally, this is equal to 2 pi. Apparently, we get 2. So B1, it is simply a number which is equal to 2. So now, this is how we can determine one of the values. So, and then we can, and by the way, it looks like all the terms of A1, A2, and more, A1, A2, A3, all of these, they're going to be 0 because we can observe that whatever value, second, this is the function. Here we can put cosine 2x, we can put here cosine 3x and more, but cosine is always an even function, x is always an odd function, so if we put here an, and this will be cosine nx, this is always going to be equal to 0. And there is a more major reason for this, which is the following. This function that we see here, this function which is defined here in black, but that we erased, this is an odd function, a fonction tech. So all the contribution from an even function, this should be equal to 0. So an even function cannot contribute to construct an odd function. For this reason, all of this odd function, we need to consider only the values of b, which are the coefficients in front of the sine x, sine 2x, sine 3x, sine 4x, sine 5x functions. So as a result, if we continue like this, I guess it was we try to make this clear how we find the a and the b's, the coefficients, and finally we can say that the function f of x equal to x, it's equal to 2 times sine x minus sine 2x over 2 plus sine 3x over 3, and it continues like this. Plus okay, so this is what you observe for the expansion of an odd function which looks like f of x is equal to x. Now, for sure, this is a true function, okay? So they converge. So this will converge to the true value. We have no doubt about this one. And what we can often, or what we can often use this is to observe actually specific properties. When we say properties, we can find, for example, that if we set x equal to pi over 2, we can find that we can write that pi over 2 is equal to 2 times, what is sine of pi over 2? Well, let's see here. This is the angle 0, this is pi over 2. Here we have pi, and this is 3 pi over 2. So sine of pi over 2, it is obvious that it is going to be 1, because we are here, 1, minus sine 2 pi, so we have pi, x is pi over 2, this is sine pi is equal to 0, so this term is gone, plus, so this will be a 0. Sine 3x, we have sine 3 pi over 2. 3 pi over 2, we are talking about here, sine is equal to minus 1, so here we have minus 1 over 3, plus, I think the next term will be 0, because the sine, it will end up in being here, then it will become plus 1, And we can construct, actually let's try to see what is the next term. This is n equal to 3. When we set n is equal to 5, we get here minus 1 to the power 5 sine 5 over 2 divided by 5. And here we are going to have the following, that this is going to be, I guess, minus 1 over 5. I hope we don't make a mistake. And sine pi, 5 over 2 is, we get 1, 2, 3, 4, 5. We get pi over 2 again. So it's 1. Okay, so this is all going to be equal to 1. So this is the next term. Now, this is one way how we can construct specific relationships or of spatial values. Okay? So, why would this become useful? This could be useful because you may construct a system, or you might need to describe a function, a number like pi, which cannot be written with infinite precision, okay, because it's 3.14, 15, 29, it goes on like this. But it is possible for all of us to write this specific number as a function of integers. Okay, so we can get integer numbers out of this, and probably for any computational unit which can accept only integers as an input, this would be a good choice. Okay, so we can expand, we can do the expansion of a specific value of a function as a function of integer numbers. So this is what we see here. And again, we can repeat the following, that if we have an even function, then we don't use odd function. We're going to use even to describe an even function, which looks like this. F of x is equal to 3x squared. This is an even function, so this is even. And if we have any other function, which is an odd function, such as f of x is equal to x, so here we have an odd function. This means that if you do the series expression of this function, we need to use only cosines, cosine nx in the expression. The coefficients that come up from the sine function, they will all be equal to 0. And for an odd function, we need a series expression which includes only terms that looks like this, sine nx. So this is